Hi, and welcome to Building Better Recommendations with Graph Analytics for Snowflake. I'm Corydon Baylor. I'm a senior manager, technical product marketer here at Neo4j. I specialize in graph analytics, both for our Snowflake offerings and for just graph analytics and for Fabric and all the different umbrella terms that involve everything graph analytics. I'm joined today by Kevin Gomez. He's a solution engineer. And Kevin, why don't you introduce yourself?
Yeah, of course. Thank you very much, Gordon. So I'm Kevin. I'm solution architect actually for Neo4j. I work for Neo4j now for roughly 4 years, I think. And yeah, I have a pretty big background in graph data science as well, graph data analytics. In the past, I did a lot for financial services, but right now I'm focusing on the verticals manufacturing and automotive.
Amazing. So, the format of this webinar will be I'll do a bit of a discussion with Kevin, and then I'm going to jump into an example. Just to kind of kick us off, Kevin, if you could tell us a little bit about where you were before you were at Neo4j and if you were working with relational data.
Yes, in fact, I did actually. Before I joined Neo4j, I was a researcher at the University of Leipzig. And I was part of the database department back then. And now you can imagine already, right, working with databases all along and doing research about them. I work quite a lot in the classical relational space, but also quite a lot in NoSQL parts as well. And yes, so I did all the painful things that you usually do: structure your data into tables, creating normal forms, all the fun things, right, that you have to do in order to get rid of duplications or to increase data sanity and quality, everything. Yeah. So the relational world I was quite used working in that part as well. But the good thing is, due to the NoSQL part that I also covered in my research, I was quite soon very familiar with graphs. Let's say it like that.
Yeah, that makes sense. I will say also personally, before coming to Neo4j, I was working as a data scientist for about 8 years, and I'll be honest, I never actually really touched graph in that time. I was pretty much exclusively working with relational data, worked SQL and Databricks, things like that. And when I came here, I was very unfamiliar, and one of the first things I did was kind of research graph algorithms. It was kind of almost a revelation, how simple these things are and how easy they are to use. So I think that's a pretty common journey for people, both just getting into graph and people who are coming to Neo4j. So just speaking to that, when you were first working in graph, how did that compare to the work you did before?
Yeah, so to be honest, when I was in the relational space active, I worked with distributed systems. Not sure if you ever heard of them, but Apache Spark and Apache Flink, for example, well-used technology today. And I was working on their data frames APIs, you can imagine. And all that stuff was already relational as well. But the good thing is, so part of my research was then to extend those systems to work with graphs. And that was actually the first touch points that I had with graphs in general. And for me, that was quite eye-opening, you could say, right? So you leave the tables behind and you start mapping your data, your tabular data, into a graph model. That is really, really interesting practice to do. And you know that all that stuff, all the painful things that you have to think about in the first place, talking about primary keys, secondary keys, normal forms and stuff like that, that just vanishes. Suddenly you just have your graph data model in front of you. You load data. Of course, you have to prepare a script for that, or back then, at least I did. And then you have the first time you see your data in its natural form, basically alive. So the feeling out of that period of work that I did back then, that was really, really nice. And that is also something that I see working with customers today.
Yeah, that makes sense. What would you say was the hardest part of shifting from a relational mindset to a more graph way of thinking?
I would say, for me, it was kind of natural, right, to shift from tables to a graph, because I always had this feeling that, hey, my data in its form is already graphy, right? Why not have it in the form of a graph. So for me, that shift was kind of natural. But when I see working with others, back then with my colleagues or with customers today, especially when you work like 10 years, 20 years, 30 years with relational tabular data, that's quite hard, right? And for them, I see like two major stones on the way that they have to come over with first. The first one is, how should the model look like? So sometimes they are really afraid of modeling their tabular data into the graph world, and they are afraid of doing mistakes in this form. And the second part is, the modeling is one thing, but also to leave this tabular world behind and to allow failures is the second part. So they need to acknowledge that you can redo your stuff, you can change afterwards after you modeled. And that is a nice and beautiful thing on the graph sides, but that is something that, when you come from the tabular world, you don't see those things up first. That is something they need to get used with.
Right. Yeah, that makes a lot of sense. What would you say tends to click fastest for people new to graph, and what usually takes a little bit longer for people?
Yeah, I would say the fastest is definitely more on the retrieval and the grabbing part. So especially when they see our query language, Cypher, or in broader sense GQL, then because of the form of queries and this ASCII style where you just draw a pattern and then you query the graph and you get the pattern back, right? So all the answers that fulfill this pattern. This is something that clicks very fast with customers. And even with non-so-technical people, when they see the query style, even non-technical people will understand what happens there. So that's something that clicks very, very fast. But the slow part, again, is this modeling approach, right? How can we get our tabular model into a good graph model? Because again, they are very afraid of doing mistakes. And maybe they are also a little bit used in working with ontologies, right? Some companies, they work with bigger research departments, and they usually propose ontologies for problems. And to build a fully built and flexed ontology usually takes time and also a lot of knowledge. But in our case, we preach a different best practice. We say, hey, start with questions that you want to answer against your data, and then create a fitting data model, a graph data model. That supports your questions first. That's usually the best practice that we preach from the Neo4j side.
Yeah, no, that makes sense. I'll say a little bit about my experience with that too. I found that graph compared to tables, like you're saying, it just feels a lot more natural. If you're like whiteboarding out how different things relate to each other, I think you're naturally going to do kind of dots and lines, which is a graph structure. What I personally found very confusing at first was when to use like a property on a node versus just a different node type. I found myself kind of almost making my nodes like just their own little mini tables with tons of different properties, whereas sometimes it's better to have a few different properties, a few different types of nodes, and avoid just like loading up a given node with tons of properties. So I think in general, customers and people, and my wife, for example, is a very obviously intelligent woman, but she's not ever worked in the data sphere. And I remember trying to walk through a SQL query and then an equivalent Cypher query. I could teach her the Cypher query like almost instantly. She could just read it and understand it. Whereas with the SQL query, it was like it was a whole lesson there. So I think people who are unfamiliar with Cypher or graph might jump into it and find that it's a lot more intuitive than they were expecting. And the same is true with graph algorithms too. I think they're a lot more intuitive than more traditional machine learning methods. But moving on to the next question. So in your view, what types of problems are genuinely suited better for graph approaches versus relational or feature-based ones?
Yeah. I mean, you can imagine that this is a type of question that I've heard like hundreds of times when I talk to customers, right? Like, what's the best cases for Neo4j? What should we put inside a graph? What not? And usually I answer with a few points to that. Like, the first point that sparks in my mind is, especially when you feel already that your data inherently is a graph, right? When we talk about networks, when we talk about pipelines of things, or supply chain networks again, right? So when you already see your data is naturally referencing each other and you have relationships between your data points, then okay, I might use a graph for that. Sometimes they still build it then on top of tabular databases, for example, and then they see what they need to do, and you guess it, a lot of joins, right? So they need to do a lot of joins, a join in order to traverse those relationships, right? And when you have a use case like this built and you see a lot of joins, usually joins, they don't really scale well, right? So it's quite painful to do that stuff. Then you should think about, hey, I might try a graph here. That's point number one. Point number two is usually a very complex data model, right? So you have a really, really complex business model. You already said it. Usually when you start at a whiteboard, usually you build a complex business model as a graph on the whiteboard, right? But then for some reason you take the stuff on the whiteboard and put it into tables. But working with a graph, you can skip that. Your business model becomes your graph data model, and that is the beautiful thing. So if you have a really complex data model, then let's try a graph, because you can fetch this complexity inside nodes and relationships very, very well. And also your management and also your bosses will understand what you're working with, because again, business model is graph data model on that part. And last but not least, so it's usually 3 points, is when, for example, graph algorithms can help you find answers to very specific problems. I give you an example. You want to check in a supply chain network, hey, what happens if supplier X drops out, right? Then you should do upfront a good analysis on supplier X, for example, with centrality algorithms. For example, the betweenness centrality algorithm will tell you something about it if this supplier X is a bottleneck in your supply chain network or not, right? And with that, you can find those answers in doing analysis upfront. And we all have seen what Corona did to our global supply chain, right? We had perfect use cases, to be honest, to counterfeit that.
Yeah, I mean, I love that phrase. Your business model becomes your graph model. I think that really captures how intuitive this type of work can be. And I mean, obviously, this particular webinar is about applying this into Snowflake, and I think we'll see as we go on in the future how easy that is too. So bringing it back to recommendations, because we haven't spoken directly towards that yet. Have you worked on a recommendation pipeline before? How do graph-based approaches differ conceptually from traditional approaches?
Yeah. Yes, I worked hands-on delivery basically for customers on recommendation pipelines. Different styles, each and every one of them, but in the main aspect, maybe you can summarize it as follows. Maybe let's start with the traditional approach, right? The traditional approach usually is what I've seen with customers before is they train usually machine learning models, right? And they are trained on tabular information, and then the machine learning model tries to infer those relationships between those data points and then comes up with recommendations, right? First, this has to be trained, right? So the data scientists on the customer side, they really need to know what they are doing. And the second thing is also, that's one of the shortcomings of this approach, is the machine learning model will not tell you why it made this recommendation, right? It will just spit out a ton of recommendations for your customers, but you will not have like the lineage information why this recommendation was done. That's usually the traditional part that I see at customers. And now when we move this problem basically into the graph world, first thing what you can do is you can materialize those relationships between customer and product information, right? So you can create this relationship upfront, which is already very interesting to see, to be honest. The last recommendation engine I did was more or less for a food company, let's say. And what we have seen there is when you have customers that are linked to products, then naturally, by just importing this data, naturally you will form communities, for example, right? And you see communities in your customers appearing in that part. And that is already interesting to see, right? And then the next step would be to use this information of communities, for example, right?
Yeah, I mean, that makes total sense. It kind of taking a broader view, just for customers who are perhaps not used to graph. So if a customer is graph curious but still somewhat skeptical, what questions should they ask themselves before trying a product like graph analytics in particular?
Yeah, I mean, for example, the point about explainability, right, that I just brought up, is usually a really good example. Like you've got your recommendations, could be easy products like in the food department, or could be really complex products like, I don't know, manufacturers of hospital machines, for example, right? When you have this type of complexity and you want to do recommendations, the question is, do you want to understand what is happening under the hood when you do recommendations, right? And which type of features do you want to put in? Yeah, is your feature set, for example, very static? Then maybe a traditional approach might work well for you. But if your feature set is really dynamic, especially in today's world, then a graph would highly make sense in that part. This example about manufacturers in hospital mechanics, for example, this is also something that I worked on in the past. And there I've specifically seen a lot of changing features, right, that they want to pull in their day-to-day recommendation pipeline. And there a graph was perfect for that. Yeah, we have specific algorithms for that available. For example, FastRP, that's one of my go-to algorithms that I want to use. And FastRP is able to capture your graph network, your neighborhood, basically into node embeddings, right? So you have a vector that represents the neighborhood of something, the neighborhood, let's say, of your customers. And with this vector available, now you can suddenly infer the similarities between your customers, for example, or on your product level. It doesn't really matter, to be honest. Both is viable to use, right? But you have specific algorithms available that will help you with that aspect.
No, that makes total sense. So finally, what advice would you give to a team considering graph analytics for the first time to avoid some sort of common missteps?
Yeah, I would say be brave is the first one. Yeah, so don't mind failures or issues. Just have this open mind idea in trying out new tech in this case, right? I mean, the learning curve of Neo4j is really nice. You have a lot of material on that part. And that means also the information about graph data analytics, or in this case, Snowflake graph data analytics part, right? You have good documentation and good trainings about this available. And you also find, not for all use cases, but for quite a lot of them, you find on our homepage a lot of success stories, right? So you will also find examples how you can implement something. And especially nowadays, when I talk with customers and they want to jump into the graph world, I tell them, hey, use the tools that you have as a company. Like, for example, nowadays everybody uses ChatGPT or similar LLMs, right? So make use of those tools, for example, that will help you with the idea of preparing your first graph data model, right? So show them your tabular schema and say, hey, I want to back a recommendation pipeline in Snowflake for that, right? So I need this mapping into the graph world. And then ChatGPT or Claude or whatever you use will help you with the first creation of your initial graph data model for that part. And then even you get suggestions of the algorithms that you can run, right? So depending on the type of recommendation that you want to do, usually I refer to them as the Amazon way of life, which is more customer collaboration, right? So I think you remember when you put something in your Amazon basket, then it will tell you other people also bought X, Y, Z, right?
Right.
That is the Amazon way of life in terms of recommendations. So if you want to do something like that, then you should focus on customer to customer similarity, for example, right? If you want to go another way, which I refer to usually as the Netflix way of life, is content-based, right? And Netflix, for example, when you watch a Western movie, then usually the next recommendation will be another Western movie, right? And when you want to focus on this type of recommendation pipeline, then you should focus on product-to-product similarity, for example. Yeah, and all those different algorithms in terms of community detection, FastRP similarity, and so on will help you solving those problems and then building a very, very fruitful recommendation pipeline.
I will say you're kind of teeing up a lot of what we're going to be talking about today. I mean, the example we're going to give is a very kind of simple one that I think helps illustrate some of the algorithms that we have. It's the Netflix way of life, where we're talking about product to product. But you also talked about LLMs a little bit. We don't have it in this webinar, but in an upcoming webinar, we've actually integrated with Cortex and Snowflake. So the view you're going to see here, we're going to consider kind of like the data scientist type of view, where you're looking at the code itself and kind of have that cemented out for our repeated use. But we do have a view where you can just ask Cortex, like, hey, here's my schema. What sort of algorithms could I run? I need to find, similar products to each other. Like, how do I do that? And it will just kind of do that for you. It'll walk you through what algorithm is picking, what it's thinking, and get results for you and save them back into Snowflake tables. So that'll be kind of more of our data analyst view of the product. But with that, I want to thank you, Kevin, for joining us for this discussion, and you're welcome to hang on and listen into our demo that accompanies this discussion if you'd like. But yeah, thanks again, Kevin. I'm going to jump in.
Thank you very much for the invitation.
Yeah, of course. No, I really do appreciate it. So with that, let's jump in. Okay. So what makes a good recommendation? Consider the humble grocery store coupon. Whenever I check out at a grocery store, if I scan my club card, there's a little machine that spits out a coupon, and that coupon is always specific to me. This, of course, is a recommendation, but how does the grocery store know what to recommend to me? Well, one approach, kind of a naive approach, would be to simply look at what items are most commonly co-purchased together. So, for example, baby spinach and bananas are co-purchased 24 times together. Or, again, these are a lot of banana-based products or paired with a different kind of produce. On first pass, we might be tempted to spit out coupons for bananas whenever a customer buys baby spinach because our data seems to indicate that people who buy organic baby spinach also want bananas. But although it is unintuitive, it's actually not a very good recommendation. So you should think of it like this. Whenever we recommend items, we should consider some items to be like hinges towards others. If baby spinach and bananas are bought together and avocados and bananas are bought together, then perhaps someone who buys spinach would also want avocados. But here's the rub. If every grocery store basket has bananas in it, then it's not a very good hinge. It doesn't provide any personalized recommendation about what else someone might want to buy. So, whenever bananas are in every basket, its presence is not a good predictor of what other items will be in that basket. It's just noise. So, if we move into our notebook itself, we can see how how graph analytics for Snowflake cuts through that noise. So the algorithm we're going to be using today is node similarity. That is powered by the Jaccard coefficient, and we'll kind of get through how that works as well. But before we run anything, we're going to need to take a look at our data. So we have two main tables that we're going to be using today. There's more tables in this, database, but we have products and baskets. So products have things like the product ID, the product name, the aisle, and the department. The baskets are basically like the grocery basket. This data, for what it's worth, was taken from an Instacart data set that was used on like Kaggle. You can find a full notebook, so you can, including like where we got the data and how we sampled it, by going to our dev guides. So if I go up to the top, you can kind of see that. And if you want to, at a different point, walk through this, go here and give it a try. So moving back, we have baskets and we have products. So the first thing we're going to need to do is do a little bit of cleaning. Actually, before that, I might cover what we have right here. So when I was talking earlier about these kind of co-purchasing patterns, you can create like a co-purchase table, and it'll give you these counts that we saw earlier, where we have, again, baby spinach and bananas and how often they're co-purchased together, all the way down to like the least commonly co-purchase items, which would be no co-purchases, of course. There is some cleaning that you need to do if you're going to be using this kind of data scientist view of graph analytics for Snowflake. Again, if you're using that Cortex view, you don't have to do any of these steps. You're just kind of asking Cortex to pick out an algorithm, but we wanted to get a little bit more under the hood for this example. Um, so you'll need two tables essentially. What we're going to be doing is we're going to have a table for nodes and a table for relationships. And our graph algorithm or syntax will create a graph from that, like a graph projection. So basically, you're going to create everything you need to describe the graph in table format, and then the algorithm will project it and run itself against that graph. So first, we're going to create our table for nodes. We're just going to be using our products table. We'll be renaming it to node ID from product ID. The graph list for Snowflake is opinionated on some of these names, so you'll have to do that. The second one is we're going to be creating an edge table, which has a source node ID and a target node ID and a weight. So this edge list is basically saying, how often is each thing co-purchased together, these two products, and the higher weight will indicate that they're co-purchased together more. So, for example, these first two are more commonly co-purchased together than these second two. That's it. That's pretty much all the cleaning you have to do to get ready. You do have to grant permissions. Kind of depends on your team setup. Sometimes you'll have like an account admin who's the one you can grant permissions, and then you'll have like a user who will actually run the algorithms. These are all the permissions you need to grant. They exist in 100 different places in our documentation, and basically it's just a control find to find the database and the schema and replace that throughout. Once those things are done, you're ready to actually run your algorithms. So the algorithms you run, they're in kind of one cell, and you're only being charged, by the way, while this cell is running. But within that cell, there's kind of three parts, right? So we have this project step, this compute step, and this write step. This project step takes those tables we talked about, right? The nodes table and the edge list, and they project a graph from it. The compute step picks out the algorithm, and the write step decides where it should live. So after we've gone through that, it's time to look at our results. I think for this particular algorithm, or for this example rather, it's most instructive to look at the items that are actually least similar to each other. So like we said, that if bananas are in every single basket, they're not a very good signal, even if they're commonly co-purchased with lots of different things. So when we look at our least similar items in our table, we find that for the top 5 least similar items, bananas show up in each one. And that kind of goes to what we were saying. Bananas, because they appear in almost every basket, they're too common to tell us anything meaningful about what else a shopper might want. Just like we predicted, just noise. And our graph algorithm was able to pick up on that and downweight them. So when a customer actually goes to check out, this can be like at the time of inference, you now have a table that has similarity scores for each product. And you say a customer is checking out with something like peanut butter cereal, organic bananas, and cauliflower, we can find that organic pepper jack cheese is actually the most similar item to anything else in the basket, and that's based off cauliflower, not bananas, as we might expect. Those are at the bottom. So now they will receive a coupon for something new, organic pepper jack cheese, and when they come back, they'll have that coupon in hand and will hopefully be incentivized to buy something new. So exactly how did that work? Under the hood, node similarity is comparing neighborhood overlap, not just raw counts. So bananas appear in a huge number of co-purchased neighborhoods, so they aren't very specific to anything. And cauliflower, by contrast, is co-purchased with far fewer items, and then many of those same items have a co-purchased neighborhood that overlaps with pepper jack cheese. And that indicates an underlying shared taste, which is why that item was selected as a recommendation. So I think Kevin kind of mentioned this, and it's funny because he said Netflix and he said Amazon, and the two examples I have here were YouTube and Amazon. But recommendations are not just limited to coupons. In fact, I would say they lie at the heart of any successful business. So all major platforms from YouTube to Netflix rely on recommendations to keep viewers watching. And major retailers like Amazon always seem to have this little string of recommended items and products to add and pad to their bottom line. We talked a lot today about recommendations, and Kevin kind of brushed on a couple different ways. He a lot of the algorithms he was using weren't these similarity algorithms for his recommendation pipelines, but more of these community detection algorithms. We have a lot of algorithms available. In Orograph Analytics, we have 65 plus, and Snowflake, we're adding more and more. This is kind of the different types of algorithms we offer. We have pathfinding algorithms, we have link prediction algorithms. So pathfinding does what you might expect. They find a path between 2 points. Um, link prediction says, okay, you got these two nodes. They're pretty similar to each other. Can we expect a relationship to eventually be drawn between the two? Community detection algorithms. So that's something more similar to what Kevin had been talking about. You're finding communities like communities. So maybe you're finding individuals who have similar preferences. And if this individual is similar to this individual, then maybe the things that they buy or watch would also like to be viewed or watched by, or bought or watched by a separate individual within that same community. You have centrality algorithms that show how important nodes are within a network, and you have similarity algorithms, which is what we just saw. It shows how similar two nodes are to each other. Finally, you have graph embeddings. Graph embeddings kind of convert the graph structure around a node into numbers that can then be used to in traditional machine learning approaches. All of that might seem very confusing. We do have a book out. It's called A Practical Introduction to Graph Algorithms. You can search that title. It's a free ebook. I actually wrote that book. It covers a couple of things we're talking about here. It covers the Jaccard coefficient, which we just discussed. It covers community detection and fast RP, which Kevin called out as well. So this will give you a lot of information, both about the math, but more importantly about the intuition behind these algorithms. That way you know when to best apply them. So, why did we build this product? Well, we wanted to bring these algorithms to customers where they're currently storing their data. Um, we believe that graph algorithms, although they work best when paired with a graph database, have plenty of value for every customer who wants to get more of their data. We wanted this tool specifically for Snowflake customers to help you uncover new hidden patterns in your data without having to move your data at all or learn a new language. So as you've seen, everything is done in SQL. There's no point where your data is leaving Snowflake. This is a Snowflake native app. It's all happening entirely within Snowflake. And I think best of all, like Kevin said, be adventurous. There's no commitment to this. We offer a 30-day free trial, and after which everything done is done on a flexible pay-as-you-go pricing. So I would suggest, people just simply go over to the marketplace, start that free trial, see if this works for you, see if you're finding new things, play around with the Cortex agent if you're unfamiliar with graph algorithms. And then after that is a pay-as-you-go process. You kind of set these jobs to run, and you won't use any more of your budget than is strictly needed to solve your problems. Yeah, and with that, I hope everyone enjoyed the webinar. I will, I think we might have had some questions in the chat. I'll go through and answer them. Or I think someone from our team has been checking the chat to see if there's any questions to answer them. And I appreciate it, and I want to wish you guys happy graphing, and I hope it works well for you in Snowflake. Thanks.